CMS architecture patterns. Should be pretty interesting. Excited to hear. Oh, yeah.
Tony's got one last thing. For those that weren't here, Tuesday we had a quick get together regarding the hackathon that's going to be partaking in October. We're just getting together, hopefully try to form teams. They're having a bunch of teams that are kind of self-formed based around common goal and idea that they want to pursue. So there's more information available that we sent out next week. There's also information on the site, info.salem.com/hackathon, I believe, as well as on the Confluence, the XM hack page. So if there's any questions there, ping me. I can get you all the information, and then some more information we sent out on Tuesday as well. So you have basically all of September as well as October to get stuff in order for that. We'll have the HoloLens devices in town on September 12th for 2 weeks, as well as again a month later during the hackathon itself. So there is one sheet out there indicating what teams have formed. I can ping that out in the group. There's a VC water cooler after this, as well as another sheet on that Google sheet indicating if you are just looking for a team. I'm not assigning people to things, because that's not really the goal of this. So either find teams that already exist and ask to join, or create your own team and ask people on the list to join. So it's kind of a choose your own adventure still. So if you have any questions, ask me. But other than that, enjoy that. It's
cool.
You, Hauser.
All right. So thanks to those of you who've joined here. It's exciting to see a number of people with different levels of experience and background. I was just moving past a little bit about being a Microsoft guy at Amazon, which is cool because Amazon runs Microsoft workloads too. But because we have a different levels of background, I think I'm going to try to strike a middle. For some people, this may be a bit beginner, and so I won't be insulted if you decide partway through that you've got better things to do. I'll try not to lose anybody who may have no experience with Amazon, so I'm going to try to just strike a balance. But if you see something that there's a phrase or a word that I haven't explained properly, stop me if you're confused or you're unsure of something. I definitely don't want to leave anyone behind. So rather than talking about like service by service, because you can kind of go out to the web and hear Amazon's pitch on each of their different products, I wanted to take a slant at this as looking at it from the perspective of different combinations of services into architectural patterns. Some of these patterns obviously are not new at all or unique to Amazon. They're good practices regardless of where you're hosting, but showing how they translate into the Amazon environment. I'm going to start with what I'll call a traditional. And this is sort of back in the earlier days, kind of pre-cloud. If you're going to stand something up in your own data center, even maybe before it's been virtualized, what did that look like? A lot of our clients definitely still operate in this mode, so it's not antiquated, but it's certainly not certainly cutting edge either. Some hard to read bullet points, that's okay because I wanted to whiteboard a little bit anyway. Regardless of where you're hosted, you're going to have a load balancer. Because if you had a single instance, obviously that's a single point of failure. So if I only had like one web server and that web server needs to be updated, or had to be powered down, or had to be patched, or whatever it is. So people solve that by saying, hey, let's go ahead and have two or more servers cooperating. It also obviously allows you to horizontally scale and be able to handle like a larger number of requests. Before the load balancer days, people would just get bigger servers. And it still is that availability problem, and you can only scale vertically so far, right? I mean, eventually, Moore's law is great, and all it keeps, more and more compute, per every 18 to 24 months, you'll double. Eventually, though, you can only get so big, and so you do hit limits there. If you can sort of scale horizontally, it's not to say that there are never horizontal limits, but we tend to encounter those much less quickly than you do a vertical scale limit. So with the load balancer, then we had a web server, in this case, let's just say there are two. And then you would have potentially, well, before I draw the lines, I'd have an app server, maybe two app servers, X number of them. Usually with the web servers, you only needed a couple because you're not, unless you're doing, a very high volume website, they just tend not to be working as hard, but you could have obviously more. Now the app servers, you could either sort of have a direct affinity where the web server and the app servers are sort of hard linked to each other. This web server knows about this app server, and this web server knows about that app server. That's not ideal, because what happens if this goes down, then essentially these pairs are no longer useful. So what you tended to do is configure essentially the connection, like a Tomcat connector or whatever, if you're probably, back in these days, it was WebSphere or VEA WebLogic or something that costed way more than you needed to spend. You would have these sort of the connections here where you sort of, all web servers need to know about all app servers. And then what happens when you add another app server? Well, I have to kind of go back and update each of my web servers to tell them this new one has come. So I've got that tight coupling, between my web servers and my app servers, which is not great because you don't want that tight coupling. I want to be able to sort of add a new app server without having to tell all my web servers about it. So then people said, well, maybe we can do something a little better where you've got maybe a load balancer in between. So the web servers kind of know about the load balancer, and then the load balancer is routing traffic. And that could be HA proxy, it could be any number of either hardware appliances to do that. This is kind of the traditional approach, hopefully nothing too shocking. Another thing, a lot of times companies would maybe put the load balancer in public facing, meaning you could just hit it from the internet, it's, it's accessible, it's routable out to the internet, and then try to keep things like the web server and the app server behind the scenes in a private subnet. The reason for that is it's harder to sort of do penetration. It's harder to exploit a security vulnerability if you can't directly access it from the internet. And if your load balancer is proxying back to your web server, it doesn't, your load balancer needs to be public facing, but your web servers don't have to be. Now, a lot of times, a more modern, what we'll see is maybe a two-tier. I forgot about the third tier here. Of course, there's a database. And back in the day, you'd maybe have just a single database instance, which the app servers are all kind of talking to. Not great from an availability perspective. What happens if you need to sort of take this database offline to do an update? What happens if you need to patch it? What if it just fails or the server that it's on fails? A lot of reasons. And also, I can't scale this out. If I had a whole lot of reports that need to read the database, they're all hitting the same database. So my read scalability is also limited in that case. So then the next step was, how can I have essentially, they call this primary, secondary, or some people call it master slave, where I've got sort of one primary database, all of my writes need to go here, but my reads could potentially come to this one, or even maybe I've just got this where all of the database is hitting here and I've got sort of a failover to this. And usually what you would do is you'd have to then configure your app servers to tell them, here are the connection strings to both copies. One is the primary, try this one first, and if that's not available, then fail over to this other one. Again, you tend not to horizontally scale or add a lot of different databases, but again, I've still got that tight coupling. It's not fantastic. So my application or my connection strings or something needs to have that logic to say, try this one first, try this one second. Or if this is a read replica, my application sort of needs to know, be able to read here and there. Okay. So another thing we see here is that the web and app server are separate. That's kind of in the traditional sense that was a common pattern. Again, the reason is people were spending big bucks on an app server, and it was licensed. If you bought IBM WebSphere, it was licensed per server, or maybe per CPU. In that case, you don't want other workloads running on this server because I'm paying lots of money for the rights to run this app server on the server. And if it's doing work other than Java App Server, for example, I'm kind of wasting some of my licensed money by having other workload on that server that's not taking full advantage of that expensive license I bought. But the other thing too is static content was kind of served from the web server, and then non-static content coming from the app server. And we'll see as we move to Amazon and we move to open source, we've tended to not worry about separating my web server and my app server. There's more tiers to have to deal with. With my load balancer and Amazon, this is called an ELB, Elastic Load Balancer. It's a service. I don't have to have a physical device anymore that I'm managing and maintaining. It's like a virtual service that I just tell it, add these servers into it, and it knows to distribute the workload across them. It'll also do the health checks of those. So I've got my ELB that's publicly facing. Security isn't a concern. I don't have to have my web server sort of in the public facing and my app server in my private subnet. So a lot of times you say, you know what, why have another sort of load balancer? Why have all this other tier here? That's, seems kind of like more complex than it needs. Let's just have a combined web app server tier. and then have those connect to my databases. Make sense? I mean, if I've got Tomcat, I can just use Tomcat even to serve my static content. I don't have to have Apache. If I want to do some URL rewriting or some other more complex authorization things that Apache gives me, I could run Apache and Tomcat even. Like I don't have to have those as separate servers. I could even combine them if I wanted to. But typically we would just deploy it. So now going back to the database tier on Amazon, I can create my own database. I can spin up a virtual machine, assign it storage, install MySQL on it, have to patch the Linux as new updates are available, have to patch MySQL as there are updates and security patches available, manage my own backups, all of that good stuff. I can do that if I want, but just like I got a load balancer as a service, if I have no special requirements, it's much more advantageous to just say, let me use database as a service. Amazon will provision a virtual machine for you. It will have MySQL or Oracle or SQL Server or Postgres or Cassandra or Aurora as the database engine on those different things. And I don't have to worry about the patching or the installation. A lot of those DBA activities become Amazon's headache. And so we like to use that as a service. We talked about not wanting a single point of failure here. So I want to have another replica. And so what I can do here is, as part of that service, I can tell it, make it a multi-AZ. What AZ is in Amazon is availability zone. Now, what we didn't talk about yet is, if these are all sitting in the same physical building, for example, like I have a data center in the Amazon Virginia, North Virginia. If these are all in the same building with the same power hookup, under this, on the same, electricity, the same potential for flooding or fire or anything like that in the same building, if there's a problem with that building, I'm going to lose my web app servers, I'll lose my database, it's all gone, and now I've had a disaster I have to recover from. What Amazon does is makes it really easy. People have probably heard of a region in Amazon. So I have a region in Virginia, a region in Oregon, a region in California, regions globally, they have many of them. Within a region, and let's just pick on Virginia, within Virginia they have multiple availability zones. So behind the scenes there are at least 3 different physical buildings with redundant power, with all these things that are sort of isolated from each other. They're close enough such that the latency between them is low. They're kind of hardwired to each other. It's a direct network connection between each of those buildings, but they're far enough away that something that would likely just take out a building isn't going to take out all 3 buildings. So I get a pretty good amount of availability and operational recovery from just using availability zones in Amazon. Now, there's a big smoking hole in Virginia because something terrible happened. Meteor comes crashing down onto Virginia. Yeah, maybe all 3 buildings are inoperable, and that's where you sort of need to consider, do I also want to have sort of my data backed up into California or something so I could fail over from region to region. So you want to think about both of those things, but it's sort of the 80-20. Most of your outages are going to be localized to a building, thank goodness, and then therefore most of the recovery will be very quick and actually transparent to your users. They won't even know. So if I do that, my load balancer, I just tell it, I create an auto scale group or set of physical instances. So with my auto scale group, I tell it what availability zones do I want servers in. I can set minimum and maximum numbers of servers. And I can tell it always have at least 2. And it will distribute them across availability zones such that if I lost that one building, the other one is still available. With the database service, I can do replication and tell it to do a multi-AZ. It's a synchronous replication, which means transactionally, data written here is guaranteed to be written here because it won't sort of commit that transaction until it's been replicated. That's only possible over relatively short distances because the speed of light being what it is, it does take information, time to travel from point A to point B, and then when you add in the networking hardware in between, you can't really go from Virginia to California and have it be synchronous replication. It just takes too long for information to go back and forth. I know it doesn't feel like a lot, but we're saying every transaction has to wait for it to be written and then be confirmed back. It's it's too far for the service to be practical. But with multi-AZ, it's synchronous and you're guaranteed to have a backup copy. You didn't have to do this. Your applications only know about the service endpoint. Amazon is dealing with the details of failing over, copying this and failing over. If this one is detected to be unhealthy, the service will automatically route your requests to your secondary. You can also do something called a read replica, which is sort of what it sounds like. It's another copy of my database used for reads. I can't write to it because I can't, the way relational databases are, I have one master. And then asynchronously, meaning eventually that data gets copied from my master to my read replica. And by eventually, it's usually half a second or less. I mean, it's very little, but it could be if I had an outage, something was written here and not yet quite here. Or if I have a read after write, it's possible that, if I just wrote to this, it's possible that if I immediately tried to read that back from the replica, it may not be there yet. It's the trade-offs. You'll see this a lot in distributed systems. MongoDB, DynamoDB we'll talk about, other different databases that do read replication over greater distances. It has to be synchronous. It has to be eventually consistent. The good thing about this is I could put my read replica in California because, again, that timing is less of a consideration if it's eventually consistent. So one way that I could protect against the 80% sort of issues of maybe one building being out is with a multi-AZ, and I can then use the read replica in California for a true regional disaster. I always want my data to be not just in Virginia. I want it to be somewhere else just in case a meteor strikes Virginia and if all my data gets lost. Any questions about sort of this more traditional on Amazon pattern? So the goal here is just to explain a little bit of the why and not just the services involved. Here's a diagram. Amazon has, I'll ping out the link to everybody. There's an architecture site at Amazon where they have different white papers and sort of different one-pagers showing you some typical patterns. One thing I'll caution is, they do a pretty good job of updating these, but there are some that I look at now and say, well, boy, in the last half a year, they've introduced some services that I might tweak a bit, but this is a pretty solid. This is showing separation of web from app, although again, we said you don't have to do that. And typically in Slalom here, we tend to just have a combined web app here. And it's showing the RDS service with the multi-AZ replication. One thing I didn't talk about, and because I was saving it for this, is serverless. So in this diagram, a portion of it here, you'll see S3. Now, S3 is Amazon's technology for file storage. It's not a block level storage, it's not like a virtual disk drive where you're doing block level reads and writes. It's more it's a crude analogy, it's more like an FTP server. You send files to it and you read files back. So it's a file. A file is sort of the atomic unit that you're sending and receiving back from S3. Just like an FTP, you're dealing in whole files, not blocks. So the idea here is if I've got static content, HTML, images, CSS, JavaScript, code files that are static. In other words, they're the same, or if you change them, you reversion it. Those can sit in S3. S3 has the capability to act as a web server for you. Because you have to have it's a REST-based interface to get input files out of S3. You're just basically posting to HTTPS to put files and read files. So you can tell it just with a toggle switch. It's really literally there's a radio button. You say, I want to be able to serve files from this bucket as a web server would. You then get a URL for your bucket. I can now use that URL. I can point it to DNS and give it a better name if I wanted to call it static.slalom.com or something like that, or static.myapp.slalom.com. I can do that. Now that host name points to my S3 bucket, and it's serving up those static files. I don't have to have a web server for that anymore because it's just all my static content is going straight to the source, to where it's living in S3. CloudFront is a content distribution network, which basically means it's going to be more efficient delivery of static files. If I'm a user in Australia and my files, my S3 bucket is in Virginia, let's say, it might take longer latency to go grab that. Or maybe it's I just had a Super Bowl ad, and millions of people are now hitting my website, and they're all trying to get the same image. If me and my neighbor and the person next to him, all in the same apartment building, are hitting the same website, there's no reason for it to go back to the origin each time. So what a CDN does is it means that there are edge locations distributed throughout the world. There's just a number of servers that it will use geographic routing. Basically, it'll find the endpoint closest to you based on latency, send your request there, and if it has a copy, great. It doesn't have to go back to the source to get it. It will just send you what it has cached. If it doesn't, it goes ask the origin for it. It now has it. That has a time to live cache on it. And then if the next person comes in and asks for it, it will check and say, I've already got it, and give it to you. So as a user, it'll be faster. And then as a site operator, it's much more efficient because your origin server, you've distributed a lot of that workload. It's only handling the cache misses. So it's got a lot less work to do. It'll scale, again, that horizontal scalability. You're adding a whole lot more servers across the world that are helping take load off of your origin. Makes sense? And we just use, you can configure it within the service to tell it what the time to live cache, or it will also respect if you have something in the header. It would just use that as the TTL. So you can also do that with, I mean, you could have an origin that's actually pointing back, doesn't have to be static content. If you had a service endpoint that's fairly, like, slowly changing, maybe I had an application that lists all of my store locations for a company. Yeah, those can change, but you know what? If I cache those for 15 minutes a pop, it probably is going to be okay if I just opened a store and I told you maybe 15 minutes later that it was actually open, right? That's a slowly changing dimension that caching might also be of value. You can have CloudFront, rather than proxying back to S3, it can proxy back to any URL. So any RESTful service that you have could also be fronted by CloudFront. So thinking about that in terms of, like, yes, it's a service, but it's a service that the data doesn't change terribly frequently. That's also a good use case. Any questions? So now the next part is, we took out essentially the need for static content, but what about dynamic content? I still have to have some compute that's running my service to give me that dynamic answer. So we've eliminated, kind of in our evolution here, we've eliminated some things here, because I've got my S3 bucket now. Let's just kind of redraw this. My request comes in. It's going to, in this case, my S3 bucket, or CDN. We'll leave out the CDN just for simplicity of the diagram. Or now there's something for dynamic content. What is that going to be? I could have it be just like we had before, where I've got a load balancer and my web app server and do it the traditional way. Or Amazon now has something called Lambda, which the John Deere team is quite familiar with, and we'll talk, there are pros and cons with Lambda. Where essentially, they call it serverless architecture, but everyone's seen the picture, right? There is no cloud, it's just someone else's server. There's no serverless architecture, it's just servers you don't see. But the idea is, let's say it's Java. I've got my Java WAR file. I upload it to Lambda, and I tell it, here's the function that I want you to run when called. And it will handle provisioning of compute for that. It will handle, based on load, scaling that out horizontally. It'll take care of patching whatever magic is running this Lambda that we don't know. I'm assuming it's Amazon Linux and Docker-like containers. But whatever that is, it will patch those things for us, right? So I don't know, Amazon doesn't publish the how it runs my Java WAR file. It just tells me that it does. So if I don't have a lot of requirements around that, if I just want my function to execute when called, Lambda is a good way to do that, because I can upload my WAR file, tell it what function to run, and it just runs it. Amazon Echo, I think some people with the Echo Hackathon did that. Also supports Node. Node's actually a really good fit for Lambda. Better fit than Java, or certainly Scala, as we've learned. I can upload my Lambda, have Echo call my Lambda. The cool thing about this is, when I'm running virtual machines, I'm being charged by the hour. Every hour my virtual machine is up and available, I'm being charged. It's not charged for every time someone's calling my virtual machine. So if I have a virtual machine that's just running all day and night and no one is hitting it, it's still costing me the same amount per hour. With Lambda, I'm being charged by the 100 millisecond increments for when it's actually running my code. So I actually have a side project when we were doing Echo. I decided to write a little note that tells me how many Divvy bikes are at the station near my house. So in the morning I can wake up and say, Alexa, ask BikeShare how many bikes are near me, and it will go out, call Divvy, and tell me, you know, there are 13 bikes available. I can also look out the window, but that's cheating. I don't want to pay. I'm cheap, so I don't want to pay for a VM, even a micro instance that's going to be running 24/7. I don't want to have to like start and stop it to say, well, I normally wake up between 6 a.m. and 9 a.m. and any of that. I just put it on a Lambda, and sometimes I won't call it for a week or two, and my bill is zero. And then sometimes I'll call a Lambda and I'll get charged like half a penny or something because I've called it a bunch. So it's great for that. It would be great for PyTV, you know, where we're not hitting it very heavily. You know, maybe in the morning PyTVs are reaching out for new content and kind of caching it locally or something like that. You know, just not having a VM running all the time. This kind of pattern of Lambda plus S3 would be really kind of a good fit for those types of things. So I still have a problem, right? If I didn't write my application to use two different host names, what do? Right? I have to either refactor my code to say all static images hit this host name, and all dynamic content hit this other host name, and route that. So now Amazon has something called, instead of the ELB, they call it the application load balancer. And this is like just announced, just released maybe within the last month. What it does is it actually does what they call layer 7. So if you think about our network stack, right, our 7 layers burrito of networking. Layer 7 is the top layer, it's like the application layer. And so what this can do is actually inspect the URL. So it speaks HTTP. It understands like a web request because it's working at a higher level. It says, what is the URL here? And you can actually define pattern matching to say, based on this, essentially translate that from /images to static.slalom.com/images. And you can do that in your application load balancer, send it to my S3 bucket, and anything else, or maybe it's /API, you know, whatever patterns you have, assuming there's some sort of pattern that you could differentiate whether it's a dynamic request or a static request. Put that into your application load balancer, and now you don't have to refactor all of your code. You're just basically building a few rules in here that do that translation. Makes sense. I'm still not having any servers that I can touch or feel. Obviously, S3, you know, is a service. There are servers that are doing that. My Lambda has to have something that's executing my code, either Node, Java, Python, etc. Oh, one other thing about that, though. If I'm going to call Lambda directly, there's something called the API gateway. And what that does is it translates a web request to invoking your Lambda for you. It's basically just a shim that allows it to call your Lambda from a web call. It does a bunch of other cool things too, but for the purposes of this diagram, what that does is it takes an HTTP request and essentially proxies it back and calls your Lambda on your behalf, grabs the answer, and sends it back to your caller. Now my database, same thing, right? In this case, if I wanted a relational database, I'm going to use RDS with my multi-AZ if I want it to be highly available. So it's not quite serverless in this case, because RDS, it actually provisions a server for you. You don't have to touch it directly. Amazon will patch it, Amazon will do all of that stuff for you, but you see it. You can see, oh, here's my database instances, here are the VMs that they're running on. Those are visible to you. If you really want to pretend this is all completely magic and there are no, you know, it's truly serverless, DynamoDB is a NoSQL database that Amazon has, and essentially it presents a table to you. And essentially it's a document store. So what it's really doing is presenting to you a key value store. And you don't know sort of what magic is making it be able to do that. Behind the scenes, it's sharded. It has a lot of different servers that are distributing your requests based on a hash key. But to you, it just looks like I've got a key value store that I'm reading and writing from. So if you really want to go kind of quote serverless, ditch the relational database and go DynamoDB. I mean, depending on your application use case, of course. If you've got a lot of relational data and you want to be able to query it using SQL, please use RDS. If you just need sort of a key value store to put your information, Dynamo is probably going to be just less overhead for you to do. Any questions about that? How are we doing time-wise here? I guess we're doing pretty well.
I have one question.
Yeah.
As traffic grows with the serverless architecture here,
Yeah.
you're eventually going to be running lambdas pretty consistently.
Yeah.
How do you decide when to bail on that and go back to
Yeah.
having a server?
One of the things it probably warrants a brown bag unto itself at some point is as we move to services instead of infrastructure. Whereas when we're dealing with infrastructure, a lot of times our only consideration, well, not only, but primarily it's around performance. With the cloud, a lot of it just becomes economic, to be honest. There are some actual constraints on, we'll talk about those in just a second, but a lot of times the first thing I would do is look at what percentage of my time do I think I'll be running Lambdas and how many concurrently, basically how many times do I think this is going to get invoked for how many milliseconds, and try to figure out what my charges would be. And then compare that against how many EC2 VMs would I need to handle that equivalent workload, trying to do a little rough math and say, just from purely financial, am I getting ripped off one way or another? Like if I'm gonna have, like if I'm gonna run Netflix on Lambdas, you know, that's a lot of requests coming in and out. I may say, you know what, that's gonna cost me more just because of the pricing model here. So then if I'm gonna be charged a lot more to do it this way, I'll hire people to handle some of the server management for me. I've got tooling I can do. It may not make sense, right? So the first thing I look at is kind of the economics of it. But then when it comes to like, are there scaling limitations, right? Theoretically, no. But the reality is with Lambda, you don't choose what kind of an instance you're gonna have your Lambda run on because it's, quote, serverless to you. With EC2, I can get a compute optimized VM, I can get a memory optimized VM, I can get an IO optimized VM, or I can get combinations of those and really kind of right size my VM configuration for my workload. With Lambda, it's just assuming all general purpose. So that's another sort of performance consideration, that if you've got workload that is doing any kind of heavy lifting, that's doing a lot of compute, probably not Lambda. Because you're not getting a compute optimized VM. If you're running it a lot of times, just the economics of it might be. There's also some overhead, frankly. Behind the scenes, what's happening here, Amazon doesn't publish exactly what's happening, but you can infer. There's a lot of container magic that's actually happening to be able to deploy your Java code into this serverless architecture. So it first checks when there's a request to your service. It will say, is this code already deployed and sort of available on somewhere? You know, assumably in some sort of like container that's running in a cluster. The answer is no. It says, okay, well, I've got to deploy a container that has your Lambda code in it that can execute. So there's a little bit of like overhead that it's having to then deploy that. And if I never call it again for, say, 15 minutes, again, it's a fuzzy number, they don't commit to a specific. But if I go a while without calling it, Amazon's going to say that memory that container is consuming is valuable. They're going to eventually unload your container and say, you're not using it right now. I'm going to free up that memory for someone else. Then if I call it again, well, guess what? I've got to re-provision that container and do that all over again. So there is a latency for infrequently called things. If you've got a super high performance API that needs to have results immediately upon the anytime it's called, that warm up period may be a downer. If you're calling it a lot of times, then you kind of look at it a little bit as what's my bell curve and can I accept the outliers? Because from a percentage, if I'm calling it 10 times a second, that warm up is going to be once every blue moon, and the rest of the times it's already resident. But as you scale up, you might have to deploy more copies, so that warm up can also apply there too. So you can have a greater variability in response times with a Lambda architecture. And then just also if you're tying it, we're not going to get into, I know I promised a bit of Kinesis, but just looking at the total amount of time and content, we'll do that another time. There can be affinity where your Kinesis, you maybe sort of have a thread affinity here to the Kinesis shard, and that will limit your ability to scale up to it. That's one of the things we ran into with GE as well. So it's not, this kind of thing, just because I have a hammer, not everything's a nail. I'm not trying to say that this would be the go-to for everything, but I wanted to make sure we're educated on it because there are some use cases where it probably makes sense. PyTV is an example of that as well. And ideally, I don't have to worry about availability, scalability, and things of my Lambda, assuming I've got fairly general purpose requirements in that regard. And Steve and anyone on the John Deere Data Lake team can give you the reels on the trade-offs, the reality. Especially it's a newer technology, it's a newer service. So yeah, on paper it's great. I don't have to worry about managing my servers, but now I've got to worry about managing my Lambdas and all that comes with that, right? So you don't ever get anything for free. So definitely have some conversations with people that are actually doing this to say, what is the real current state of this and how is it improving and is it ready yet or not for like real production workloads? Any questions? So this is a picture I stole from Amazon, just showing what I just drew on the whiteboard essentially, showing the API gateway. Again, it's showing CloudFront as that CDN. And in this case, it's actually, it's showing it as being, kind of all things going through CloudFront, and then it would be proxying back to Gateway or S3. That's another way I think you could do it. Although I want to well, assuming that if this came from Amazon, it must be right. Although maybe it's recently been changed, but API Gateway kind of uses some of the underlying technology that CloudFront does, because Gateway will also do some caching if you ask it to. So there's some weirdness of actually interoperating with CloudFront and Gateway just because of that. It was kind of overlapping on itself. It was a little bit of almost like recursion within Amazon. So don't quote me on this. If this came from Amazon, they must have fixed that. We're running low on time. We've got about 20 minutes, so thought we'd do a little bit of a lightning round of some other topics, just to kind of whet your appetite, introduce you to some of the concepts, and then who knows, if there's interest, I'd be happy to come back and do deeper dives on any of these individual technologies. Anything that you were hoping to hear in the next 20 minutes that you would walk away angry with that I'll talk about? No? No tomatoes being thrown? Okay. So one of the things I wanted to point out, this is illegible, I didn't mean for you to read it, and I'll send out a link. There's a Architecting for the Cloud AWS Best Practices. It's a white paper. It's undergone a number of revisions over the years. This version was published in February, so it's pretty current. It's not super long. I mean, you look here, it's 39 pages total. It's a good read, and it does, it walks you through just general principles that are good to consider for architecture, as well as then how do they translate, how do they apply in the cloud world. As we kind of walk through that whiteboarding exercise of evolution from that traditional model to sort of more the latest cutting edge model, we saw that the first round was basically translating what we used to do on premise into the AWS services, right? And then people realized that with new capabilities come new opportunities. And let's rethink a little bit that architecture. Like, do I have to separate my web and app server? Do I have to put my web server in a public subnet? Those are some of the basic obvious questions. And then, over time, we kind of say, how do I scale horizontally? And then auto-scale group and things. So the patterns that we apply are different in the cloud because we have different capabilities. We have different constraints. Not that we don't have constraints, we just have different constraints. And some of the constraints we had on-prem, are no longer applicable. The number of VMs I can spin up. How many do you want in the cloud, right? So I tend to favor horizontal scalability over vertical scalability, because if you need if you need more VMs, just add another one. Don't try to get bigger and bigger boxes, because that big box could fail. Then what do you do if it's running half of your traffic because you just had two very big boxes? Well, I can't have all of my traffic onto that one server, and I can't get a bigger box that would handle all of it, so I'm kind of screwed, right? So we favor horizontal scalability in the cloud. And then as we're moving, we're trying to say also, we're starting to favor services at a higher order services over virtualized infrastructure. While if I have special requirements, I could do my own load balancers. I could sort of create virtual machines. I need more of them because they need to sort of cooperate in case one of them went down. So I'd have to get multiple virtual machines. I could run HA proxy on those. I could have them essentially clustered and communicating and trying to figure out who's alive and who's dead and all that good stuff. Do I need to? Right? If my use case is handled by the application load balancer or elastic load balancer, why would I roll my own? What's the added value for that extra complexity that I'm introducing? Sometimes you have to, because you're like, you know what? ELB does it. And the Click project, I think, ran into this with some of their unique requirements of kind of handling the way Click was communicating server to server, they kind of had to do their own load balancing. For them, it made sense because the service didn't do what they needed it to do. If the service does what you need it to do, start there because it's just less that you have to do yourself. So anyway, really good read. I encourage everyone to just check this one out. So high availability. Amazon. I think it was Werner Vogels or Werner Vogels. I don't know. The German pronunciation leader.
It's probably Werner.
Yeah. His mantra was, and I disagree with the literal translation of this, but he basically says everything fails all the time, which that would mean that projector would be always failing, as would my laptop. So it's not that everything fails all the time. It's that at some point in time there's something failing, and at some point in time that's going to fail, right? I think that's what his quote is shorthand. Any component in your system, I guarantee you at some point it will fail, and at any given point in time something could be failing. So design for that, right? Our traditional architectures, when we were doing things all on premises, we had constraints, right? We only have one building, so I can't put things in different availability zones. So I just kind of hope that this building doesn't go down. If it does, maybe I've got a DR center somewhere else, but I don't have this sort of active design amongst availability zones. But now with the cloud, because of the scale of the cloud, Amazon is building separate buildings that are geographically close to each other with synchronous replication latency between them. So take advantage of it, right? There's really now no excuse for designing in those single points of failure. So look through your architectures where, I drew one single bucket here, right? So you can say, well, Matt, what happens if this fails? And of course, an entire service can go down. It has happened. But behind the scenes, there are a lot of different components here with a lot of redundancy built in across those multiple availability zones. Amazon is hiding that complexity from us, but in reality, this S3 service is a highly available service that has been designed with redundancy, without single points of failure. So again, I ask myself, who do I trust more? Me to design it, or Amazon to design these services? They've got, as much experience as I've had in systems, they've got a lot more. This is what they do. And so I tend to say, use a service when you can. It's the same reason why you might favor code reuse over. If I've got a library that a lot of different projects are using, it's probably been debugged pretty well because, any of the weird odd edge cases, someone probably has hit it if it's a mature library that's been out there a while that a lot of projects are using. Same concept applies of service versus rolling around. Okay, so I didn't draw any sort of back-end processing in this diagram before, but I do want to touch on it. So we talked about wanting to have loose coupling, and what does that mean? We talked about at the very beginning where I didn't want to have my web servers have to know about all my app servers in order to route. That was tight coupling. I had looser coupling by introducing the abstraction of a load balancer in between. Another concept can be, let's say I've got a website, and when you come in and you register on your website, my website, at some point in the not so distant future, I want to send you an email thanking you for visiting and registering with my website and sending you some more information via email. We've all been to sites that do that, right? I've got two options. Well, maybe I got probably an infinite number of options. Two come to mind. One is my app server. When I get that request, I can immediately kind of reach out and send an email as part of my service that's running on that app server and send a response. And send the email then, and then sort of tell the user, thank you for registering, we've sent an email. That's one option. Chances are that email, they're not waiting on that email immediately. It's not like I'm sending you your password reset, or even if I was, they're probably not waiting for that immediately for that page to refresh. It's probably good enough to say, we'll be sending it very soon, look for an email that contains this information, right? So I want to do that asynchronously. And so what I can do is I can have my app server that got that request drop something into an SQS. It stands for Simple Queuing Service, and it's a message queue. People have probably heard of RabbitMQ, other MQ services, MQ series, I think. So what it's doing is it's dropping a message into this queue, and it's dropping, maybe a bunch of them. And then what I have is I've got a group of workers, and this can scale horizontally. I can have like an auto-scale group of workers that, depending on how many messages are in here, I can say add more or take some away from this pool. They can grab a message, process it, and then it's done, right? So here I can scale this out as big or as small as I need. If for some reason my email capability was down, my email service was down, or I had maybe a single point of failure on a single SMTP server or something, these messages are still here waiting. I haven't lost them. It's not like my service is unavailable. It just means there's a little bit longer between when my users get that email and when they were expecting it. But my website is still up and available. I've broken sort of that tight coupling between sending that email and my application service. Make sense? So the reasons I would do that are scale independently. Maybe these have different types of servers than my app server. My app server may also do a lot of compute. Maybe I need a lot of CPU on my app server. Sending the email, no, pretty general purpose. It's probably not even memory optimized. It's just cheap. So get a bunch more of them, scale them up horizontally. So that's why I use message queuing. People were doing message queuing long before the cloud, but it's still a good idea where you can do synchronous with queues and message queues, but it gets a lot more complicated because you essentially have like a publish subscribe, and it gets harder. So the dead simple use case is if it's something that can be done offline to do it there. Won't talk about this in detail, but Amazon also has something called a spot instance, which can be up to 95% cheaper than an on-demand instance, where essentially you put in a bid and you say, I want to have X number of VMs with these characteristics or these types of VMs, and I'm willing to pay 3 pennies an hour or whatever my bid is. If the current market says that that's a fair price based on supply and demand, I will get those VMs, until which point my bid becomes not above the market price. So I only pay the market price, but my instance will keep running up until the market price exceeds my bid price. So another thing is that I really don't care exactly when these things happen. It could happen overnight in a batch, or hey, it's great if it happens sooner. I could have this spot instance where I have my bid that's pretty cheap, and saying as long as before these things have to go out, I'm pretty confident my bid will be successful. I can have these workers come and go, read from my message queue, and do very, very cheap batch processing based on sort of this message queuing paradigm. It doesn't have to be emails. You could think of it as being, file, like video file transcoding, or any number of things that maybe aren't super time critical, but you want to do on the cheap. That's a great way to do it.
Do the workers need to be VMs, or could they be something like Lambda?
They could. You can have basically Lambdas are great for triggering. So I showed them the one context of being triggered by the API gateway, being called explicitly. But you can also think of Lambdas as being like back in the old days, people used to put database triggers into databases, like when this data was inserted or when this data changed, call this stored procedure and have it do execute a function on that. Microsoft has sort of taken that idea to say a file lands in S3, that could trigger a Lambda. A message is landed in SQS, that could trigger a Lambda. Data's dropped into Kinesis, that could trigger a Lambda. So there are a lot of different things. Think of Lambdas as also being the glue that Amazon is building between the different services. So you can have, rather than polling, it can be essentially triggered event firing whenever these things happen. Yeah. But you certainly could do Lambdas here. You usually see Lambdas compared more with like Kinesis. This is I think, frankly, better suited because you could sort of do different scaling, and you tend to see it more with like still EC2. Elastic Beanstalk is a service we didn't have time to get into today. It might even warrant combined with another thing. It makes it super easy. You upload a WAR file to Elastic Beanstalk, and you tell it, rather than being a web tier Beanstalk, make it a worker tier Beanstalk, and then you tell it essentially the ID of the queue. Beanstalk will automatically pull the queue, and when there's a message in there, it will actually use an HTTP post. It will post it to your web service for processing. So your web service then doesn't really have to know about the queue. It just knows the payload. Like, it just has to understand essentially what's going to be in the payload of the message, and that will get posted as a HTTP post So then I can process that. That's a great way to do this loose coupling, is just write a WAR file, tell Beanstalk to watch this queue, and it will horizontally scale things for you. It will add more workers based on your queue depth, and it will shrink the worker pool as there are less messages in the queue. Any other questions? Okay, time-wise, we have 5 minutes. We good to go for a quick explanation of containers? Literally be like 3 minutes, so then you prepare any slides. So I didn't want to leave this out. So we talked about virtual machines, we talked about Lambdas, we talked about different things. What about Docker, Matt? That's also a pretty hot topic in compute. So Amazon supports Dockers. They have a service called ECS. It's the the EC2 container service. And EC2 stands for Elastic Compute Cloud. So, what this is a Docker cluster management. So you can have a number of virtual machines that are part of your cluster. You can have registered different images, and then essentially what you do is you define tasks that say, roll up into services that say these different container images are all supporting this type of workload. It needs to be deployed and run on servers to actually be executed. And you can obviously run things locally, on your laptop as a Docker container. Then you can upload those up to Amazon ECS and then run them in the cloud. For clients that are kind of saying, hey, I kind of worry about lock-in, I want to use Amazon, but I don't want to do anything proprietary, maybe that's an answer as well. The other cool thing about that is with like Elastic Beanstalk or EC2, I really have one VM per workload. And maybe I've got microservices now where I'm having, each service is doing a lot less. And I want, even a small VM feels like overkill per microservice, perhaps. I can have a cluster of servers, and then, multiple Docker containers can be running on a given VM, and it makes a little more efficient use of my servers. But I still have that encapsulation of my workload via Docker container. ECS is relatively new. Again, I think it was announced maybe last year at reInvent. So it's probably still not as feature-rich as, say, like a Kubernetes or some of the other ones that are out there. But again, it's as a service. Look at it, say, does it meet my needs or not? If it does meet your needs, again, it's probably simpler to just use the service. But you always have the option of deploying your own cluster and cluster management and doing whatever you want. It's just more software for you to manage. Any other questions? Yeah, Avi.
So going back to Lambdas for a minute.
Yep.
So you mentioned that if you don't use it for a while, it gets offloaded from memory, so it's
Yep.
going to be slow to start up again. But if you're using it constantly, it can be really expensive.
Dependent, yeah.
What kind of applications does it work really well for?
Yeah. So really expensive. I guess I would want to caution that depending on the type of workload you have. Some of the things it doesn't work very well for are compute intensive, things that you need sort of massive scale on that you're doing, say, high disk releases especially. There's additional latency, time certainly from the time that it's not spun up. So all of those things kind of looking at and say, can I sort of tolerate those edge cases?
There's also a time limit?
Yeah, there's a 5-minute time limit for execution. So I guess I was kind of lumping that in with compute intensive, but if you're doing a lot of work, there's a certain amount of overhead to making it biting off a small amount that can be processed in a fairly short amount of time. And it's sort of like if the overhead of instantiation, processing, response is, if you have to chop it up to a very small amount, that overhead becomes a greater percentage of the overall work being done. So factoring that in could also be a consideration. Certainly, you're not going to process large amounts of data in a given Lambda. The idea is you handle given events with the Lambda. And maybe that Lambda event trigger is commissioning a job that's running in EC2. If you've got, say, a big file in this Lambda in S3, you're probably not going to process that big file in your Lambda, but the Lambda is great to be that glue to say, an event has happened, there's a file. What I'll do is I will call my web service running on my EC2 instance. It's compute optimized, I've got a lot of them. I'll tell it that there's a file here. Go pick that up and go process it. It's sort of the idea there. So yeah, it's finding that sweet spot, it's still a little bit up in the air. Node has a lot less warm-up time than Java and Scala because it doesn't have to sort of create the JVM and get that all initiated. So a lot of times, if I'm doing something that's like an API and I want to do it in Lambda, I think Node is probably a better choice. It's not, a lot of APIs may not be that CPU intensive, generally speaking, and yet I want them to be available more quickly, even if they haven't been recently called. Yeah.
So you mentioned like right out of the box, AWS offers technically lower high availability replication for your databases. Does it do something similar for directory servers as well?
Yeah, there are. Yeah. There are a whole lot of services I didn't talk about today. There is a directory service that you can use that would be a hosted directory service in AWS. There are a lot of options for directory. You can federate, another directory. There's also a token service that you could call out to something else and use that as like a authorization check and say grant you a temporary set of credentials based on, let's say, authenticating you to a federated ADFS. So there are a lot of different options for that type of, especially for directory services for authentication, authorization use cases. But yeah, that's the same ideas. I would prefer to use that as a service than trying to roll my own. But a lot of companies, if you already have like an Active Directory, they just sort of have that replicated in the cloud. Cool. Thanks everyone for coming. Appreciate it.